I want to verify the mean value theorem, right? So first of all, is this a continuous function on this interval? So what's the only thing that would cause a problem here? Well, 0 or negative numbers, right? And we don't have that here, so it's good, it's continuous. And then let's take a look at the derivative. So to do the derivative, I think what I'm going to do is before I do the derivative, I'm going to rewrite this as 2x to the negative half, like that. Right? That's what this function is. Bring that square root up as a negative 1/2. I'm doing that so I can apply the power rule when I take the derivative. So my derivative here would be bring the negative 1/2 out, so you get negative x to what power? Negative 3 over 2. Negative 3 over 2. Which we could look at as negative 1 over the square root of x cubed. Right, so x to the negative 3/2, you drop it to the bottom as x to the positive 3/2. Oh, we still have a negative there, so it'd be negative on top and then this, and then I converted that into this. All right? All right, so that's my derivative. Is this a nice derivative? Is it well behaved? Well, not at 0, right? But again, we're not looking at 0, so we're not worried about that. This derivative should behave very well. And so the mean value theorem should apply. So I want to find a c, right? At least one of them, such that the derivative at c is equal to f of b minus f of a over b minus a, right? That's what I'm trying to find. So I'm going to work the left and right hand sides of this. What's the derivative at c? Well, there's your derivative, right? Plug c into it. That must equal, okay, this part's going to suck. You know what, let's do something. Just because we can't. Let's make this on the interval 1, 9. That'll just make our algebra easier. It doesn't change anything else. Is that all right with you? It's going to make plugging in a little bit easier for us. Let's go 1, 9. It doesn't change the fact that it's defined there, right? This derivative's still defined there. Nothing changes. So when I plug in b, I'm going to be plugging in, what, 9? Subtract what I get when I plug in 1. And then divide that by 9 minus 1. What do you get when you plug in? What do you get when you plug in 9 into the original function? 2/3 minus what happens when you plug in 1? You should just get 2 over 1, so 2, and then all of this over 8. Questions? How are we doing on time? All right, so now let's figure out what that is. That's negative 1 over the square root of c cubed equals, yeah, let's figure out what this is. This right here is on the top. When you do 2/3 subtract 2, you could rewrite 2 as 6/3, then over 8. That minus that is 4/3 over 8. Or sorry, minus 4/3. You go with me? And then when you divide by the 8, it's the same as multiplying by the reciprocal. So what do you get there? Negative 1/6. Negative 1/6. Now you have a couple of options here. You can cross multiply, right? Multiply here and here. Hey, what happened to my negatives? Yeah, I just multiplied both sides by negative 1. Got rid of them. Almost there. Trying to solve for c. Square both sides. And now cube root both sides. So from here, cube root of 36 equals C. And the cube root of 36 is not a number we can find easily. We'll need a calculator for that. On your calculator, you can go 36 raised to the 1 divided by 3, and that'll give you the cube root of 36. Questions? I'm going to try and draw this again. When we plugged in 1, we got, what was it, 2, and then when we plugged in 9, we got 2/3. Those are the two endpoints. And let's see, I need my m to be, did anyone try that on their calculator? Cube root of 36? I don't think I can do it here. 36 raised to the 1/3. Oh, it did it. Awesome. Without me actually doing it, does it look to you all that I have found the point between 1 and 9 that the tangent line would be equal to the line connecting those two? Does that look pretty parallel to y'all? I could probably exaggerate it a little bit to kind of really convince you. Right? Imagine connecting these two with the line. It looks like it's parallel to that. So we have found that, yeah? Okay, we still got more to do. This problem is going to look like it's out of nowhere, all right? This problem is going to look like, what? Like, where did this come from? I want us to show this equation has exactly one real solution. So I need to be clear on what I just put up there. I'm not asking for you to solve that equation, all right? I'm not asking you for you to solve it. I'm asking for you to show me that there's only one real answer to this. When I say real, meaning real number. There could be some imaginary number solutions, or complex numbers. Show me that this only has one real solution. Right? That's like, where is this coming from, right? What does this have to do with the mean value theorem, right? So here's the first thing I'm going to have you consider. We talked about this months ago, something called the intermediate value theorem. It's a way that you can check at two endpoints and see if your function goes from positive to negative or negative to positive. And then if it goes from positive to negative or negative to positive, then you know it must pass through 0, right? If it's a continuous function. So by looking at this, can anybody think of a number that I could plug into this and get a positive number out? 1? 0? 1 would work as well. What do y'all want to use? If I plug in 0 here, 0 cubed is 0. E to the 0 is 1, right? Ignore this for right now. What I'm asking you to do is consider the left side of this. I should have said this first. Consider the left side of that equation. Just look at that function, all right? Forget that this is equal to 0. Look at that function. I want to know when that function is 0, right? That's what this is saying? So I want to know when that function crosses the x-axis. So first thing, plug in a number and show me that you get a positive value out, and then plug in a different number and show me you get a negative value out. And then somewhere between there, it has to go through 0. So what did you say? 0? 1? And then 0, right? Which one do y'all want to do? 1 or 0? Doesn't matter to me. 0? Okay, so if we plug in 0, we get 0 cubed plus e to the 0. 0, that's 0, right? Plus e to the 0 is 1. So I get a positive number out, right? I get a positive answer there. So graphically, here's what we have. At 0, this is up here at 1, right? If I were to graph that as a function. All right, now, is there anything you can plug in and get me a negative answer out?
Anything greater than -1.
Well, how about -1 itself?
Yeah.
Let's try -1. What happens if you plug in -1? You get -1 cubed, right? Plus e to the -1. All right, -1 cubed is -1, isn't it? Plus, now e to the -1 is 1 over e. And if you get on your calculator and do 1 divided by e, this number is smaller than 1. So when you put these two together, you're going to get a negative answer. Now, if you don't like that, plug in -2 and it'll work. Or -3, -4. So what we know is that at -1, here's -1, we get a negative answer. Y'all understanding so far? We did something like this before. We used what was called the intermediate value theorem. This is a continuous function. It's continuous because it's a polynomial plus an exponential, which, remember what e to the x looks like? There's no jumps or breaks in the graph. So when you put those two together, this is a continuous function. So I know when I plug in -1, I get a negative number, right? This is a negative number right here. This whole thing is negative. That's positive. So when I plug in -1, I get negative. When I plug in 0, I get positive. And if the graph is continuous, it's got to go and cross through here somewhere, right? Is that enough? Are we done? Show me it has exactly one answer. So right now we know it does cross through here, right? But what if it does this? Right? It could have 4 answers, right? It's saying to show that it has exactly 1. You understand? So right now, where we are at this point, okay? The fact that it switches from positive to negative, all that tells us is this. That tells us that we have at least one solution to this equation in the interval -1 to 0. I have at least one, right? At least one. This says that there's only one, and we need to show there's only one. So you ready? Here's the big idea now. This graph, let's say it had 2 answers, right? Let's say it had 2. Then it would have to go up, come back down, go back. Oh, well, actually, yeah, it could just touch, I guess. Touch and go back up. Wouldn't that have 2 solutions in there? Right? Do you have a comment? Okay. That could be happening, and we need to prove that that's not happening. Right? We need to show that this is not happening. That it goes through, cuts through only once, right? Well, look, if it hits it twice, do you agree that it's going to have to go up and come back down? And then go back up? Which means the derivative would need to be positive, and then it would eventually have to be negative, and then go back to positive, right? But look at the derivative of this function. What's the derivative of this function? But, right, the derivative of this function is, give me the derivative. 3x squared plus e to the x. What can you tell me about this? No matter what x you ever plug in, what is it? Positive. Because this squared, right, times 3, that's always well, it could be 0, couldn't it? That could be 0, but it can never be negative, right? And that right there must always be positive. If you think back to what e to the x looks like, right? Here's e to the x. That graph is always above the x-axis. So this, at the worst, it could be 0, but if not, it's a positive number. And we're adding to it, that has to be positive. And when we add those 2 numbers together, this must be positive. Which means that the derivative, right? The derivative is always positive, right? And if the derivative is always positive, that means my graph must always be going up. If it turns back down, the derivative at some point would have to be negative, but that's impossible. Got it? So those two conditions together, the intermediate value theorem, because the graph changes signs, the intermediate value theorem guarantees us at least one answer, one solution, one x-intercept, but the fact that the derivative is always positive, that tells us there can only be one. Make sense? That's kind of interesting, right? We didn't use the mean value theorem there at all. We used just the idea that the derivative has to be positive and that then it can't turn back on itself. All right, any questions? You have to do one of those for homework, right? There's a problem like that for homework. So it's kind of weird, like what do you do? Well, first you have to show that you go from positive to negative, which guarantees at least one answer. Then you have to show either the derivative is always positive or always negative. And then you're done. Any questions? All right, here we go.
We have one question over here.
Okay, good. What's your question?
So if the derivative is negative, does that mean it has like multiple solutions, or is there like two solutions or three solutions?
Good question. So remember, we had a point here, right? Here's the x-axis. We had a point here and a point here, right? And we knew that when you connect from here to here, you're going to have to go through the x-axis. So we have at least one answer. We then determined that our derivative was always positive, right? So if that means that it can't do this, right? Because then in here, do you see I have negative derivatives? And so this is impossible. It always has to be going up, right? The graph has to always be going up. So that would verify that our graph can only cross through one time. If you had gotten this, that the derivative was always negative, right? Always less than zero, that should make you think there's a problem. Because to get from here to here, you have to go up, right? And if you're saying the derivative is always negative, that means you're having to always go down, which doesn't make sense. Now, had you started the problem and you did this, and you found a point here and a point here, and then you showed that the derivative is always negative, then you could guarantee me that there's only one answer. Is that answering your question? Does that address it?
Yeah.
Whatever the derivative does should match what's happening here. Like it shouldn't be in conflict with what you're seeing.
So we're only going to get problems that ask for one solution.
Exactly one solution. There's only one problem in the homework.
Can we just draw the graph? Maybe like here.
Okay, so yeah, I mean, if you graph it, it's obvious, right? Yeah, it's obvious. But the point here is, can you do this without a picture? Like, can we use what we know about the derivative and what the derivative is telling us, right? The derivative, the next section is all about this. Is all about, if the derivative is negative, what does that tell us? The graph's going down, right? If the derivative is positive, what does it tell us? The graph is going up, right? So this is our first problem where we're trying to like really investigate what the relationship between the derivative and the shape of the graph is. And graphing it would just circumvent all of that and not use any calculus, and anyone could do that, right? So there's a big debate. Most of what we do in calculus we could just do on a computer. We could just graph it, we could find the highest and lowest points, and there's a debate like why not just do that? Why do all this? And I think there is a place to have a calculus course probably for like biology majors, not engineers and not math majors and not computer science majors, people who are not going on to do more math, where we do calculus with computers, right? And we don't get into all the stuff that's real messy, and we just say, hey, look, let's graph a function. Oh, let's find the highest and lowest points, right? And then we could do some like cool problems, cool applications, and have zero understanding of calculus. That make sense? Does that idea make sense? Like, you don't need to figure out how to take a derivative or set it equal to zero. You just use the computer to do all that for you. And I think there's value in that, because in the real world, that's probably what you would do, all right? But at the end of the day, you still have to remember, like, somebody needs to know how to do this, right? Like, the person who writes the program and solves for that point, like they need to know how the calculus works, right? It's not some magic thing. I don't know if did I tell you all that? I have enough time. Did I tell you all that story about one of the classes I took in graduate school about the computer program? Okay, I didn't. So there's this really dangerous idea in the real world that happens with engineers, architects, I mean, just all over the place. We become so dependent on computers. It's this black box idea, all right? So I took this class in grad school, right? And the idea was this. Some person needs to build a bridge, right? And so they need to figure out structurally, like, you know, how big does this beam need to be? And so they start feeding numbers into a computer, right? They feed in all the specifications, and then the computer spits out an answer, right? Here's the answer. And the engineer says, okay, go build that. This is what we need. We need the beam to be this long, this thick, blah, 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 use this metal, right? The engineer has no idea how that all happened, right? Just that this is the answer. So we trust this answer, right? We trust it. We trust people's lives on this answer. So this is basically the question goes into this computer. Something happens within the computer, you get an answer, right? So this class I took, what we had to do, it was a project that we had to finish by the end of the semester. It was a class called numerical analysis. And so what we did was we had to go pick one commonly used program, one program that's used, you know, throughout the world by engineers or mathematicians or whatever. Go pick any software you want. And we had to feed it a problem that we could theoretically by hand get the correct answer to this. So we could show without the computer we could get the answer and prove it and be watertight with our answer. We had to figure out a problem, we had to come up with a question that we could get this answer and then feed it to the box and get a wrong answer. So we had to exploit the weakness of the software. And we had to use the software to show that you could feed it something that it screwed up on and prove the correct answer. Does that make sense? So that was our project, yes?
It's kind of like that question that we had a while back, that like when we put it into graphs, sometimes it said like that there was no solution, or like it just said error.
Yeah, I mean, yes, a little bit deeper than that though. We didn't want to get error. We wanted an answer. We didn't want error. We wanted, you know, here's the problem, give me a solution. Oh, x equals whatever. It's wrong, right? Does that make sense? So
say there's an error
when there really
actually
wasn't.
an answer.
yeah, it doesn't say anything's wrong. It just gives you an answer, and just we know it's wrong. We know it's a wrong answer, right? That was the project, right? The program I used, or that I did that on, was Wolfram Mathematica, which is the program that I use all the time, because I had to learn I had to learn the weaknesses within that program in order to use it. So Wolfram Alpha, you know, you go to the website Wolfram Alpha? No?
Yeah.
Okay. That Wolfram Alpha is based on a computer program called Mathematica. So you go to the website and you type in a problem, it actually goes to their server, their kernel, the thing that actually does the computations, and that's called Mathematica. You can buy that program as a student at a student rate. As an educator, I get an educator's rate. If I were just a person in the real world, I'd pay probably $1,000 for it. Was there a question? So anyways, this is getting back to your question. Why don't we just graph it? I get you. Like, I understand. Like, why not? I mean, just most of the time, this is okay. We can never disconnect ourselves so much from the theoretical part of math and calculus that nobody actually knows what's truly right and wrong anymore, right? We always have to have the people who are intimately connected to the pure math, right? And at the end of the day, this is a math course, and there is a path through the math to become a math major or a computer science major where we have to understand the theory, right? So that's the argument to always make sure we keep at least one foot on base here, right? We don't want to completely be like trusting the computer for everything, right? All right, am I going to have time for this? 8 minutes. I'm going to try. Okay.
Are you going to show us how it works?
That's what I'm going to try for. Okay, so we need to agree on something first. If I give you a distance function, do you all agree that the derivative is the velocity or speed? Yes? Okay. Let's take the two cars. The first car is going to do something, right? The second car is going to do something. They're going to go and they're going to tie, right? Okay, what I'm going to do is I'm going to call this the first car here, I'm going to call it f of x, all right? And the second car I'm going to call g of x. And I'm going to use x instead of t. We were using t for time, right? But here x is going to be time, all right? So x is our time. All right, they start and they stop at the same place, right? I want to show there exists a C in the interval AB. Let's just make the beginning of time A, even though that we know that that's 0. Let's just call it A, and then we'll call this n time B, right? I want to show you that there exists some point C in here, right? I don't know where it is yet, but I need to show you that there's some point in there, that there exists a C in there, such that this is true. The derivative at that C for f is equal to the derivative at C for g. Would y'all be satisfied if I show you that? That somehow there's some C in here that the slope of the tangent line for the f function will be equal to the slope of the tangent line for the g function. And it will happen at the same value C. So if I can show you that, you're happy? No one would complain? All right, so the way I'm going to do this is going to be weird. I'm going to I need to leave that up there. I'm going to be able to do this. I'll have time. All right, what I'm going to do here is oh, perfect timing. That thing, the screen timed out. It's like it knew I needed that. All right, so here, this is the thing that really, no one's going to ever really come up with this on their own, all right? I mean, not no one. It would take you probably a while to figure this out. I'm going to create a new function. Out of nowhere, I'm going to create a new function. Here's what it is. Let, and I think I'm just going to call it, I don't know, capital M of x. I don't know why I used capital M, all right? Let capital M of x be equal to f of x minus g of x. So I've created this new function, right? I'm calling it capital M. And all it is the difference between these two functions. It's that function minus this function. That's all it is, all right? Is that all right with you? Mm-hmm. Okay. So do you agree, first, M is continuous on AB? Well, these cars, right? These cars, the path they travel on, it's not like the car like vanishes, right? And then comes back, or, right? It's a continuous path, right? So these are both continuous functions. So if I subtract two continuous functions, I should still be continuous, right? The difference of two continuous functions is still continuous. So that's continuous, right? The second thing, M is differentiable on AB. Well, again, if the derivative of f is just the speed and derivative of g is just the speed, then that means that both f and g are differentiable. And so the difference of those two functions should be differentiable as well. Y'all buy that? Like, I don't lose anything by subtracting two. I don't like all of a sudden create a problem with the functions. All right, now here's the big thing. Third thing, M of A is equal to M of B. That's the big thing. So I'm going to graph over here M. Okay, I'm going to graph the M function. Here's at A, right? And here's at B. What's the value of M at A? So if you go here, you take the F function, subtract the G right here. They're both 0, aren't they? They both have the same value. So the difference of those two should be 0. So I have this point right here, right? And then what happens at B? Well, they're tied, aren't they? So if they're tied, the difference of the two is 0 as well, right? So here's what this function looks like. Here, they are at the same place. Here, they're at the same place, right? And so m, when I graph it, is going to start here and end here. And then what happens in the middle, I don't give a shit, right? Like whatever m does, it does. Because Rolle's theorem now tells me what? At some point in here, what? What's 0? At some point c in here, what is 0? The derivative of what? M, right? The derivative of m, right? So by Rolle's theorem, you see this word, these two words, there exists? In mathematics, we write that all the time. We hate writing it, so we use that instead. We write a capital E backwards. That means there exists. So by Rolle's theorem, there exists a C in AB such that what did you just say was true? There's a C in here that what would be true? The derivative of m would be 0, right? The derivative of m at that C would be 0. I'm almost there. I need 30 seconds. Everyone's on board? All right. But the derivative of m at C, right? Well, let me do it this way. Yeah, let me do it this way. Derivative of m at C. Well, if I ask you to take derivative of m, right, take derivative of this, you would take derivative of that, right? How do you take derivative of two functions being subtracted? Derivative of each one separately, right? So that means that m prime of C, which equals f prime of C minus g prime of C, right? That right there, this right here has to be what? 0. So that f prime of C minus g prime of C has to be 0, right? Move this to the other side. Move that to the other side. And what do you have? What you told me that I could show you and prove to you and you'd be happy. Right? You told me if I could prove that this was true, you'd be happy. Yep. And I did some weird shit that you never would have thought of. And then I figured out that this derivative of m has to be 0 at some point c. But then I said, remember what that is though? That's this, right? So that has to be 0. And if that has to be 0, then if you move that over, that there's some point c in there where they're equal. So y'all were right, but that's the proof of it. Okay? All right, so for homework, do your homework problems for 4.2 that are on the schedule. Just try those problems. There's not many. There's 1, 2, 3, 4, 5, 6. There's 7 problems, and I did the 7th one in class. I already did it. So not many. Make sure you've done 4.2. Anyone that wasn't here last time, we moved the exam till November 15th. All right? Was it 15th?
I thought it was 17.
That's right. I was seeing if I was getting a reaction. It's November 17th. November 17th is our next exam. All right? Okay, everyone. Have a good day.